Hello, I'm Anna Mackay and this video is on finite geometric series, where we've done arithmetic series just before that. So looking at the proof, or how we arrive at the formula for this, so just absorb this. It's a sum of a geometric sequence. So we have all the terms in a geometric sequence and we're looking at the sum of them. So the nth term, as we know from our formula for a geometric sequence, is the first term multiplied by r, which was the ratio, that's the ratio between the terms, to the power of n take 1. So to work out a geometric series, we're going to add up all the terms up to the nth term. Now, another way of looking at each of these terms, the first term is t1, the second term is the first term multiplied by that ratio. The third term is the first term multiplied by the ratio squared. Remembering that this is the n number subtract 1. So if we're on the third term, it's to the r to the power of 2, which is 1 less than the term that you're after. So if we're going all the way up to the end, thinking about what our nth term would be in terms of t1, we have, sorry about the odd error that you get on your screen there, our nth term is the first term multiplied by r to the power of n take 1. That must mean the term before that is 1 less. So if it was n take 1 term, then the power will be n take 2 because that's 1 less. Moving on. If we were to multiply through by r, this is a technique that we're going to do just to tidy it up a little bit. The first term multiplied by r, that's fine. Second term, and so on, noticing that the powers of r are increasing. At the end here, if you multiply through by r, what will happen is the powers will simplify. The term before will be 1 less as well, and so on. Looking at that section of it as a section, what does that roughly look like? Have you seen that before? Look at the line above. Look what matches there. We've got quite a bit of matching there. So you could say it's nearly Sn, but it's Sn with a little bit more there. So if we were to take Sn and get rid of the first term, then they would match. And that's going to be useful for this proof. As we said here, isolating that t1 term. If we then shift that t1 term to the other side of the equals, so subtract it off both sides, then this section here matches that. So we can substitute Sn take t1 into this formula. Let's do that. There we are. Now we're left with this section. Now ultimately, what are we solving for? We're solving for the sum. Let's do some tidying up here, but we've got Sn on both sides of the equals currently. Let's collect them together and tidy them up. Perhaps I've jumped ahead of myself there, but so we've subtracted Sn from both sides, and on the right hand side we're left with the t1 plus t1 r to the n, rewriting that just slightly so that we don't have a leading negative, and the highest power of n first. Factorising out a common term. Sn is common in this section, and the t1 is common here. We then take this r take 1 and divide through, and that is giving us the formula for the sum of a geometric series. Okay, there's another version of this that you can use. Apologies for the font there. The other version is you just take that, but you just write it in a slightly different order, and it's useful in different settings. What I mean by that is this one is useful when r is less than 1. So if we're dealing with a fraction or a negative number, that sort of thing. So we're going to do an example using this version of the formula and this version. Just a note, if r is equal to 1, thinking what happens here, if you substitute that into the formula, these are all the same. And we actually end up with an arithmetic series, because r is 1, if the ratio is 1, that means they're multiplied by 1 each time, which means it's staying as term 1. So it's just n lots of term 1 for the sum. And a side note here, make more sense when you get into infinite series a bit more. If adding the first n terms of an infinite series, it's called a partial sum. An infinite series is infinite, it goes on forever and ever. So you can't add that up, so to speak, but you can add up a certain number of terms, and that's called a partial sum. 2 examples. Find the sum of 2, 6, 8, 54, and so on up to 12 terms. So we're going to use our formula. We're going to use our SN formula. This will all be written out neatly shortly, but I'm just showing you my thinking. So what terms do we need? We need the first term, and for that we have 2. We're going to need an R, so that is the ratio between them. So what's the ratio to go from 2 to 6, and then from 6 to 18, 18 to 54? We're multiplying by 3 each time. And N, we want up to how many terms? 12. So we're just going to substitute these in. T1 is 2, R is 3 to the power of 12, take 1, over 3, take 1, working that out, 531,444. We'll do one more. Finding the formula for Sn, the sum of the first n terms of this series. So we don't know how many terms that we want, but we need to write a formula for it. So the series is geometric. Well, so I've worked this out for you. So T1 is 9. You then have to think of, sometimes you have to work out the ratio yourself. How do you go from 9 to -3? But then from 3 to +1. So because that sign is changing, we're going to have a negative number. And essentially we're dividing by 3 each time, remembering that dividing by 3 is the same as multiplying by 1/3. So that's how we would work out our ratio. You ask yourself, well, which version of the formula should I use? This one. So all that's changed is the order of that bracket. The tip that was given is if R is less than 1, this one here is good to use. And R in this case is -1/3. So let's use this version. So we have our T1 is 9, 1 minus R, which is -1/3. Very important to have those brackets, to the power of n over 1, subtract -1/3. And when you tidy that up, that 9 divided by 4 on 3 becomes 27 on 4. Keep those double negatives. You can't change that into a positive, in case you're tempted. And just a note here, the answer cannot be simplified as we do not know if n is odd or even. So thinking about that with negative numbers, that if they're odd or even, how many you've added on, that's going to depend on where you end up. Okay, so make sure you like this video and subscribe to the channel, and the final one in this series is about geometric series, infinite series. Thank you.